Okay, believe it or not, here we are with the last lecture on chapter 16 about carboxylic acids and esters. So hopefully you've become experts in the carboxylic acids and the esters so far, and you can't wait to learn more. Now that we hopefully have the naming conventions down for the esters, it's time to take a detailed look at the properties of esters here in this lecture. We talked about boiling points of the carboxylic acids as being very, very high and a particularly important feature. If we look at the boiling points of esters, you'll notice that they're higher than for alkanes of similar mass, but they're actually lower than the alcohols or the carboxylic acids of similar mass, mainly because carboxylic acids and alcohols have the OH group there that allows them to participate in hydrogen bonding with themselves and with other hydrogen bonding molecules. When we're talking about boiling point, it has to do with how the molecules interact with other molecules of their same type. And because the esters, like the ethers or the ketones, or even the aldehydes, they can't hydrogen bond with themselves, so therefore they tend to have lower boiling points than alcohols and carboxylic acids of roughly equal molar mass. So here we see butane has a molar mass of about 58 grams per mole, and its boiling point is about 0 degrees Celsius. If we look at our ester that has about that same molar mass, a little higher at 60 grams per mole for methyl methanoate, it's an ester and its boiling point is significantly higher than the alkane. It's about 32 degrees Celsius, but still much, much lower than the 1-propanol. The alcohol that's also 60 grams per mole has a boiling point of 97 degrees Celsius, and then even higher still for that ethanoic acid, which is also 60 grams per mole. Being a carboxylic acid, it has a 20-degree higher boiling point even than the alcohol at 118 degrees Celsius. So while they can't hydrogen bond with other molecules of their same type, esters are soluble in water when they have a relatively small number of carbon atoms because they can form hydrogen bonds with the water, right? The carbonyl oxygen is partially negative. It has those lone pairs that can interact with the partially positive charge of the hydrogen atoms in the water. However, they're not as soluble as the alcohols or the carboxylic acids of the same number of carbon atoms, and the solubility decreases quite a bit with an increase in carbon atoms, starting with carbon 6 and higher being essentially only very slightly soluble or insoluble in water. Let's look at some chemical reactions of esters. First, we'll look at acid hydrolysis of esters. So in acid hydrolysis, an ester reacts with water to produce a carboxylic acid and an alcohol, and a strong acid catalyst as well as some heat is required. Notice this is just the reverse reaction of the reaction we just talked about, esterification, how we formed these esters in the first place. Now we're just breaking them down with the same conditions. It's an equilibrium process. We can just adjust it to try to favor the equilibrium in that forward direction now. So methyl ethanoate or methyl acetate plus water in the presence of an acid catalyst and some heat will go back to form ethanoic acid or acetic acid by common naming, plus methanol or methyl alcohol by common naming. So there we have it, just the reverse process of esterification is acid hydrolysis of the ester. Let's pause here for a learning check on that. So we have aspirin stored for a long time, may undergo hydrolysis in the presence of water and heat. What will be the products of this reaction? So if we look at the aspirin molecule itself, if we were going to cause the ester group to undergo acid hydrolysis, what products would we get from aspirin? Stop the video here while you put your reaction together, and then once you have your reaction equation ready to check, please start us back up. Good luck. Okay, so there we have it. We would break it there at the ester functional group. We wouldn't touch the phenyl ring, the benzene ring. We wouldn't do anything to that carboxylic acid. We would just break the aspirin ester linkage there and put the H from the water onto that O that we broke the CO bond, and then put the OH onto the C of that carbonyl. So there we have now in acid hydrolysis of this particular ester, acetyl salicylic acid, or aspirin as it's more commonly known, we generate salicylic acid plus acetic acid. So if you've ever found one of these old bottles of aspirin that's been in wet air and has gone bad, so to speak, by undergoing acid hydrolysis, you'll notice a vinegar type odor from the acetic acid. The salicylic acid doesn't have any notable odor because it's a solid, but the acetic acid at that room temperature and pressure will volatilize to quite a notable degree so that you can detect that odor. If you had trouble with this, please do check the homework set and additional reaction end of chapter problems, and then certainly reach out to me if you're still struggling. Okay, so instead of acid hydrolysis, let's talk about base hydrolysis, or saponification as it's more commonly known. It's the reaction of an ester with a strong base. So before we looked at the ester reacting with a strong acid to reform the alcohol and carboxylic acid. In this case, we're looking at the reaction of the ester with a strong base to produce the salt of the carboxylic acid. We won't have the neutral carboxylic acid here because we're in strong base conditions, so we would undergo that basic deprotonation of the carboxylic acid to make the carboxylate salt, and then the neutral alcohol. So if we look at the example here on the screen, we have methyl ethanoate by IUPAC naming, or methyl acetate by common naming, reacting with sodium hydroxide, one of our strong bases, in the presence of heat. Notice it's not a reversible reaction now because we have that strong basic substance. We're going to force it in the forward direction, and we're going to make sodium ethanoate, the sodium salt of the carboxylic acid, and then methanol, the alcohol, methyl alcohol by common naming, that was went into the formation of that particular ester in the first place. So we call it saponification because it's a soap-forming reaction. So the base hydrolysis of long-chain fatty acids produces these acid salts called soaps. And we see here, if we take a typical fat, a triglyceride, we'll talk about lipids in an upcoming chapter, in the presence of a strong base, we'll go ahead and form the alcohol. In this case, because it's a triglyceride, we form glycerol, which is a triol, right, a 3-hydroxyl group alcohol, plus 3 moles of sodium carboxylate. In this case, it depends on the particulars, of course, of the carboxylic acid. That's a long chain carboxylic acid there, as most soaps are, and you get a nonpolar tail, a hydrophobic portion from that long chain of CH2s until you terminate with a CH3. You get the polar head group from the carboxylate end, the carboxylic acid that's been deprotonated. So you're able to stay soluble in water, have those tails all come together to form a nonpolar portion, and then that nonpolar portion can attract the dirt to itself, and that's how the soap cleans. So if we take a look here again, just like I mentioned in the previous slide, that soap contains a nonpolar end that dissolves in nonpolar fats and oils, and then a polar end that dissolves in water. And you form these groups of soap molecules called micelles that will dissolve in the water. They'll be washed away along with the dirt or oil or fat or whatever the stain was, the thing that was dirtying the clothes or your hands or whatever needed to be washed. And you can get these really neat micelles. The micelles can make big spherical structures, or they can make rod-like structures. They're very interesting, and they go well beyond just the action of soap, but this is the particulars in an introduction to organic and biological chemistry. That's the easiest one to describe here. So the cleansing action of soap is a result of these saponification reactions to break down a triglyceride into the fatty acid salts and then the glycerol. So if you've ever touched a strong base, hopefully you didn't, because it's not good to do, but if you have ever done that, or even a weak base like ammonia, if you're cleaning the windows with ammonia-based glass cleaners and you're not wearing gloves, or you happen to get a little on your skin, you probably notice a slippery feel. That's because you're forming soaps. It's a base plus your triglycerides in your skin are forming these soaps, just like we talked about in the saponification reaction. Okay, so we've covered a lot of territory. Before we leave our chapter here on carboxylic acids and esters, we have one final learning check, and your task here is to write the condensed structural formulas, or better yet, the skeletal structures of the organic products when methyl acetate reacts with each of the following. So show the reaction for the products of water and an acid catalyst reacting with methyl acetate, as well as potassium hydroxide reacting with methyl acetate. So pause the video while you finish those equations and figure out those organic products, and start it back up when you're ready to check your work. Good luck. Okay, so there we have it. If we have water and an acid catalyst, well, we'll just regenerate the alcohol and carboxylic acid that went into making methyl acetate. And in this case, that would be from the acetate part, we get acetic acid, or ethanoic acid if you prefer IUPAC nomenclature. And from the methyl portion, we get methanol. If we look at B, we have now the strong base, so instead of getting the neutral carboxylic acid, since there's a strong base around that proton, the H from that COOH group is going to be removed, and therefore we're going to get the salt, the carboxylate salt. In this particular example, it's potassium acetate, as well as the neutral alcohol, so we get that same methanol that we see above. The big difference is in water, we remain a neutral carboxylic acid and neutral alcohol in the presence of a strong base like KOH, we're a carboxylate salt instead of a neutral carboxylic acid, but still a neutral alcohol. So hopefully that went well, and if it didn't go well initially, hopefully you understand now where you may have made a misstep. If that's not the case, if you're struggling with these reactions, please do try some additional ones, give it a little more time, but if it's just frustrating you even further, please reach out to me for some help. Otherwise, if things are going well, as I hope they are, we'll see each other again for Chapter 17. Good luck.